So last time we were talking about the Henry result that the spectra of the n states W plus and minus are the boundary of essential spectra. And here, okay, here's my W minus to W plus X W graph. To remind you, our operator L is linearized around a stationary wave. If we just freeze and look at the constant limits and look at their spectra, at the spectra of those constant solutions, in our case, we actually know they look like this, like parabola. That these will, number one, we proved part A, the curves lambda j of ik of limiting spectra, of spectra or the limiting states, which, by the way, is the dispersion curves given by the Fourier symbol. Those are in the essential spectra. That was part A. And now the more important part for us is to show that to the right of these, there is either all essential spectrum or else only resolvent and point spectrum. That's what we want to show. And to do that, finally, we need to know something more about the resolvent equation and spectra. Okay, so before I do this, I'm going to take an excursion to some asymptotic ODE theory, because the resolvent operator is the solution of an ODE. And okay, so we're going to now develop two very important results for us. The first one, which is something proved with so Capitula and Sandstede. And these are essentially simultaneous, not in 1998. And it's called, we named it, we gave it a catchy name, called it the gap lemma, and that caught on. Okay, so I'll explain the name after. Okay, so let A of xp be a constant matrix plus theta of xp, and theta is order of e to the minus little theta x in k derivatives on, so this is for x on the half line. And p is a parameter. So I'm thinking of this, of course, I'm thinking of the resolvent equation, which is an example of an ODE of the type we're going to look at. So, okay. Okay, so, but there are also other parameters, right? Besides just the frequency lambda, there are model parameters, and it might be important to be able to change these. And let's see, and now let B plus of P be an eigenvector of A plus with eigenvalue mu of P. I'm going to move over. Then the first order ODE, which is dxv equals A of x P V, has a solution V of xp equals Vp e to V of P e to the mu of P x times identity plus, let's see, I guess I said that in the wrong order. Well, okay, let's just write it like this. Okay, minus theta tilde x. And this is for any, let's see.
Yeah, that's some technical problem with the guys, so.
Oh, thank you. Can you, oh, okay.
The camera doesn't.
Okay, maybe. Let's see. No, we've got turn off and on. Better?
So I don't think it's frozen, but the camera doesn't show that last board. It only shows the first two.
Oh, okay. I need to go to number 2.
Ah,
Yes, we can see.
yes.
Okay. Good. All right.
Thank you.
Mhm. You're welcome. Okay. Yes. Oh, actually, I do want to write it like, okay, so this is the constant coefficient solution. That is, if we just crossed out theta here, that would be an exact solution of the ODE. So the idea is near any, so if we have, we've assumed that this is exponentially decaying, and so long as we have have exponential decay, this says we can find solutions that are near the constant coefficient, the limiting constant coefficient solutions. And here, this is for any, okay, let's see, and just say, B plus of P e to the mu plus of P x. So it's just matching these guys, right? And where for any theta tilde less than theta, and this is connected to the issue I had the other day. I definitely need to give up something here.
What's theta tilde?
Theta tilde is just a matrix. It's a matrix function. It's just I'm going to get let's see, maybe I should just say
That the answer for this.
this is the ansatz, this is the ansatz for the solution. And
Does it test some property?
let's see, maybe I need to just let's see, what do I want to say here? I want to say it's a little more Yeah, okay. Let me just say, it's easier. Let's just put it like this, where yeah, it's maybe better to write like, let me write it like this. So it's v plus of p e to the minus mu e to the mu plus p x, okay, plus order of v plus of p e to the mu plus of p x times e to the minus theta tilde x. I'll just write it like that. This is really what I want. For any, and this big O depends on theta minus theta tilde, and it's going to blow up as I let these come together. I can't just take theta tilde equal to theta. Everything would explode. And where the solution is as smooth in P as are A plus, V plus, and mu plus. So whatever smoothness I have in the parameters, I will inherit it in the solution. Okay, and this is closely related to a result that can be found in Coppell, asymptotic ODE book. In his setup, theta is just L1, not exponentially decaying. He gets a similar result. But in order to get, but for his result, he needs a spectral gap between mu and the remaining eigenvalues. And so this lemma is basically saying exponential decay can substitute for a spectral gap. So it's called the gap lemma because of the absence of a gap. It's the opposite. Right. Okay, so but the proof, it's really very similar to the proof in Coppell, but it's actually somewhat simpler. It's harder with only L1. So we're taking advantage of the fact we know we have exponential decay almost all the time, and we want a little, that gives us more information, and we want to take advantage. Okay, so the idea is we're going to do basically fixed point mapping. So contraction mapping. And the Lyapunov-Perron setup, which is used in all of invariant manifold theory and all kinds of fixed point setups. So the idea here is we're going to set up, okay, let's see. So we write dx v minus a plus of p v equals theta of x p v, and we'll consider this as a forcing term and use the linear solution formula, variation of constants, but with different starting points for different parts of the solution. That's Lyapunov-Perron. If you start at one point and treat the Cauchy problem, that's just variation of constants, I suppose. But if you do this, then I like the term Lyapunov-Perron. So I'm going to set V I'm going to try to find V equals TV. This is the mapping. And that is going to be defined as V plus very important start. Without loss of generality, mu equals 0. I can just do an exponential change of coordinates in X to make mu equals 0. And I haven't lost any of the smoothness, right? I just, A plus is converted to A plus minus mu. That's the only change. Okay, now what I'm looking for is something that's stationary at infinity. And so here's how I prescribe the stationary part. And now I'm going to integrate out to plus infinity the A plus of P x minus y. This will be less than 0. And so what I want is something that's kind of unstable, because I'm integrating back from infinity towards back. So here I'm going in the backwards direction. I want things to decay, so I want the unstable manifold, but actually I want not just unstable, I'm going to say weakly unstable, which I'll define below. This is this projection onto the weakly unstable eigenspace times theta of x p v. So this is theta of y p v of y dy. And then I subtract the integral from m to x of e to the a plus x minus y. And this is now greater than or equal to 0. Pi strongly stable, theta of yp, v of y, dy. Okay, so what I've done is for the weakly unstable space, I'm going from x out to plus infinity, and I initialize at plus. I'm basically initializing at infinity, integrating down toward x. This is what I choose to happen at plus infinity. I don't want anything blowing up. I want only the neutral mode to remain. That's my prescription. And then the strongly stable, well, okay, that's fine. I don't have to.
The letter at the end of at the bottom of the integral.
M.
So
Yes. Okay. So what I'm going to do now is I'm going to restrict. Yeah, I forgot to say, restrict to x in M infinity, M large. So I'm going to try to construct it just out near infinity. If I can do that, I'm fine, because I can integrate then backwards to 0. If I find a solution out near infinity, I can integrate it back towards 0, and any exponential bounds I have will just accumulate some large constant in front of them, because this ODE does have a bounded flow from M to 0. It may be large, but it's bounded. So I really only have to control things out near plus infinity. And if I do, I'm done. That's important, though, because I'm going to leverage this. So, okay, so this is actually, so it's not 0. I apologize. It's M. So now I'm looking at from M to infinity. And I will need M to be large at some point to get contraction. That's the trick. Because why? Well, that makes theta small. I mean, it's pretty clear why I want to do that. Otherwise, it could be quite large. I would have not really much control at all if I don't restrict it somehow, because I have a big constant in front of my assumption. This is all that's driving the contraction, and the big O is a constant. It could be large. I didn't say anything about that.
big letter.
Yes, and now, yes. Yeah, there are two projections, so okay, and these are projectors or eigenprojections onto the subspaces with, okay, the first one is, so mu weakly unstable is greater than negative theta tilde, strictly greater. And mu strongly stable is strictly less than negative theta tilde. Okay, well, how can I be sure this happens? Well, it's okay for a dense set of thetas. If I happen to choose a theta tilde that landed on an eigenvalue, I can't do this because I didn't allow for equality. I want a strict difference. But okay, if I hit one I don't like, I'll bump it a little and have another theta that's stronger. So it's no harm, but it makes it so I don't have to write as much. Okay, so yeah, so there's some strategy going on, right? So if you had a spectral gap, you'd actually you'd do much the same, but you would just have a zero here, and life would be a lot harder. But you'll see this is going to work out nicely for us. Okay, so basically, a nice way to think about this is project the original equation onto these two subspaces and treat them separately. I've effectively, I've diagonalized the system. It's coupled only through the forcing term, which I'm treating as known. So I diagonalize that as well. And now one of them I start from infinity and integrate into x. The other one I start from m and integrate up to x. And okay, and that's it. And I'm going to, yeah, that's all I need. And I could take anything I like. I could have initialized almost anything I like, I believe, at m. It would be okay, but 0 is good. Let's see. X is larger than m. Yes. Yeah, I'm going out. I'm keeping only the very asymptotic part.
What's V plus?
Oh, V plus was I'm just the plus is just to indicate I'm on the positive half line. And V plus is just an A plus is just the limit at plus infinity. V plus of the matrix. V plus is an eigenvector of that matrix of the plus matrix. Mu plus is the eigenvalue. So all the pluses are together at plus infinity. That's the idea. Sorry. Yeah.
X goes to plus infinity.
Yeah. So for now, we're just basically dividing the problem in two parts. We're just going to look on half rays because we can't, there's no reason to know what's happening near 0, right? We can only know what happens near infinity because all we've assumed is exponential convergence to infinity, at infinity. In between, anything could happen. So this is the best we could do. So that's what we're going to do.
On the other side with W minus on.
Yeah, we will the same now. We'll do exactly the same, but you just yeah, you flip the whole argument. There's no difference between plus and minus, except that I need to choose one. So I feel like going in the positive. Think positive. We're not gonna glue. We'll have a matching condition. Yeah, and the matching condition is just that they match. They do match. Right? They have to exactly match. If we're looking for solutions of an resolvent equation or an eigenvalue equation, we insist that they be continuous across 0. So that's going to be the match. But that comes in a minute. So let's see. So let me now show contraction.
Hi,
So
Kevin.
yes.
So is it okay that this theta tilde, negative theta tilde be a spectrum? So it's okay?
No, it's not okay. I'll yeah. In fact, I've excluded that by saying these are my requirements,
Oh, this your
Okay,
requirements.
but it's really also a requirement on theta tilde. If I happen to accidentally have a theta tilde that hits an eigenvalue, I'll take a slightly larger value of theta tilde that is still less than theta. I'll carry
Okay.
out the argument for that one, and it implies the other one.
So what if it's a essential spectrum and everything are continuous? Would that like there's no diff so
Oh, right now, this is not, okay, this is an ODE.
okay.
Now I'm really thinking about the resolvent equation. The resolvent equation is a finite dimensional ODE. It's just
Okay.
a usual ODE. So this is a result that I'm going to use to analyze the resolvent equation.
Okay.
So yeah, so right here we've gone from infinite dimensions down into finite
Okay. So only point spectrum.
Yeah,
Thank you.
yeah. So there's no essential spectrum. The only spectra are the eigenvalues of the matrix A plus.
Okay.
And
Okay.
A plus is finite dimensional.
Okay. Thank you.
N by N matrix. Yeah, I probably should have emphasized that, I guess. Right. Okay, so now we want to prove contractions. So we look at TV1 minus TV2. Okay, and we take the just soup norm. Contraction is what we're going to get. Okay, so this is less than or equal to. Okay, so integral from x to plus infinity e to the a plus x minus y pi weakly unstable times theta of y dy. And then I'm just going to pull out v1 plus minus v2, the soup norm of v1 minus v2. I'll just pull out of the whole thing because that can come out of the integral. It's the supremum over the whole domain of integration from m to plus infinity. Okay, so yeah, let's I should write it more carefully. It's the supremum over m to plus infinity of v of x. Just the usual soup norm that we use for most ODE things. Of course, for invariant manifolds, it's often a weighted norm, but this is even easier because we removed the growth and decay that we want. We're just looking for a stationary mode, so we just work in the ordinary soup norm. Okay, so we've got this. The V plus is gone. It subtracts out. The constant term is gone. And all we have left is integral from m to x of e to the a plus x minus y, pi strongly stable, theta, of y dy, and again times v1 minus v2 norm. And this comes out really nicely. Okay, so okay, less than or equal to. Now I'm going to use the fact that, okay, because I made these assumptions on theta, I have growth and decay bounds on e to the at. I know that the weakly unstable will be bounded by a big constant. That's why there's a c here. And I can put e to the theta tilde x minus y, and then theta of y dy. See, I'm going to actually pull out a big constant times v1 minus v2, and then the rest. Okay, and for theta, but I'm not even going to put theta because I'm going to put my bound assumed on theta, which is e to the minus theta y dy. Let's see. And this is, okay, but this is minus theta tilde. And then I have plus integral from m to x of e to the minus theta tilde x minus y, e to the minus theta y dy. And what I'm using is that this is, let's see, this is less than or equal to 0 here, and this is greater than or equal to 0. And that's where I get my two bounds. And the interesting thing is, these are exactly the same expressions. It's very funny. So, and that's what greatly simplifies this argument. So it's just integral from m to plus infinity of e to the minus theta tilde x minus y. So actually, let me pull out I'm going to pull out what I want, which is the x part, the part not in the integral. And I have e to the theta tilde minus theta y dy. That's all that's left. And this is negative. Y is positive. This is bounded. So that means I can actually, I'm running out of board. So I just cross this out and put it in with the C. But now I notice, well, actually, I do know, you know, I want C times e to the minus theta x to always be less than 1/2. So I have contract, or less than, strictly less than 1. But I can achieve that by going back and re-choosing m, because x is bigger than or equal to m by assumption. So this is a large argument here. So no matter how small theta tilde is, I can make this times, I can make c times e to the minus theta x be uniformly less than 1/2, say. And then it's a contraction. So somewhere I had to use that I was out near infinity. But yeah. It's actually, so that's done. I said some other things. I said smoothness, you inherit all the smoothness and things like that. That's true for any contraction mapping with a parameter. Yes. Yeah, so this one, okay, so let's see. Yes, those are projections onto, so for instance, the weakly unstable. If I wanted to be strongly unstable, this would be greater than 0. But I want to allow my neutral mode that I want to be in there, so I can prescribe it at infinity. I'm going to also allow some more, because it doesn't harm anything in the estimates.
What's the definition of projection?
They're onto the eigenspaces whose eigenvalues have these properties. Yeah, of A plus. The eigenspaces of A plus that are associated to these eigenvalues. The ones that grow or decay very weakly, and the ones that decay, well, I'm calling it strongly, even though this might be small, but it's decay strictly. And then I have this is a non-strict growth.
Let's think what square do you have
Okay, so for the unstable ones, it's because I'm going backwards. Yeah. And the other one is going from the one from, let's see. That's what's saving me here. Okay, this is going out to plus infinity, right? And this is,
Hypothesis on the.
on the, on that it's growing, let's see, that in the backward direction, it would, if it were strongly unstable, it would be exponentially decaying in the backward direction. But it's not, it's just not growing too fast. See, this is exponentially growing, but not too fast. And it's being saved by this. But the funny thing is, I mean, I probably wrote 4 or 5 versions of this before I noticed these are exactly the same. You can just put them together. And it's interesting to look at Coppell's version where the two are different. They're inherently different, and you have to treat this one pretty carefully. It's a harder proof. But this one, it just becomes very simple. If you have exponential decay, life simplifies a lot. And you can prove more. And we were in a, Gardner and I and Capitol and Sandstetter were also, we were in scenarios where we needed more. We could not accept, we didn't have a spectral gap, and we still needed to define such a thing. And so, yeah. And you'll see, you know, one of those cases is stability of viscous shock waves. You're going to see where this comes in handy. But right now, it's just a convenience. We don't really need it for what we're doing today. Okay. So that gives us a way to very, you know, kind of arduously construct all the solutions that we want. We can make, we could go eigenvector by eigenvector and construct these things and then put them all together to get an expression for resolving. And this is what I did for many years.
Oh, it plus then get nearby eigenvector with the same eigenvector.
Well, no, because it's not in, it's perturbed by a function in X, right? Well, you get something with the same growth rate, let's say. If you want to call that an eigenvalue, but it involves the integration of the ODE. Yeah, it's a solution. It's not an it's a solution to the ODE. Yeah, so which is more. It's not merely an eigenvector of A of XP. It's the solution of the ODE that has this property. That it asymptotically behaves like the constant coefficient limit, which we would like intuitively to think. But we need to prove it. And so this is one proof that's pretty flexible. Okay, what about any questions online? Gia, I hope you liked seeing Lyapunov-Perron. You gave us some lectures back home on using this method. Okay.
Yeah.
All right. Okay, so everyone okay with the lemma? It's, you know, it's not so unusual, right? Just that it's a kind of special situation. Let's see, where am I? Okay, so now, so I used that lemma for many years until Metivier and I found a great improvement to that. So here's, I'm going to give you another one, a corollary. It's actually quite an immediate corollary, you'll see. And this one is Metivier. And this is in what, 2004. So a bit later. And we called it the conjugation lemma. Okay, so now, and I claim this is a huge improvement. So A of XP equals A plus P plus theta of XP, same setup. And this is a finite dimensional ODE. Theta is order of e to the minus theta with no tilde x in k derivatives. K is however many we need, and okay. In k derivatives, k x derivatives, and say j p derivatives. Which could be, and so it can extend up to, if it's analytic in P, we will inherit that. That's important. Because we used analyticity of the resolvent with respect to lambda, we used that plenty. We definitely need that property. Okay, then there exists a coordinate transformation. So we'll set, oh, I'm sorry, the ODE, I didn't write an ODE. And the ODE is dxv equals a of xp v. Again, there's a coordinate transformation. If I take v equals t of xp z, and t is the identity plus theta tilde, and theta tilde decays like e to the constant times e to the minus theta tilde x, any theta tilde less than theta, the same key assumption, such that the equation in z is constant coefficient. I see a plus of p c.
The same neighbor.
It's the same setup, but a much better result. It includes the other result.
But the A plus is the same A plus.
Same A plus, but now I didn't assume I don't have to know the eigenstructure of A plus. I just say I can find a change of coordinates so I like to say it like this. It's like an analog of Floquet's lemma. Floquet's lemma says if you have a periodic coefficient ODE, there's a periodic coefficient transformation that changes it to constant coefficient. This one says if you have an exponentially asymptotically constant ODE, there's an exponentially asymptotic coordinate transformation. Oh, sorry, asymptotically exponentially decaying coordinate transformation that converts it to constant coefficient. So it has the same, right? And these are two, really big applications, periodic things and things that are asymptotically constant. Other than that, things get, a lot harder. So this allows you to treat that case. Now, if I want to come up with this function v of xp that I did before, I would just take the exact solution of the constant coefficient equation, and I would apply the coordinate transformation, and I would get it, and I have the same bounds. So it's immediate to get the other one, but it's better because what if I don't have all eigenvectors? What if I have a Jordan block? Or, other strange things. What if I'm looking at, what if I Fourier transform in some other direction so that I'm looking at a family of resolvent ODEs that may change their eigenstructure dramatically through Jordan blocks and other things. All those kind of topological changes, they're subsumed in this. Okay, so I think you can see that it's better and it implies the old one. But here's the really funny thing. The old one implies this one almost trivially. It's a trick. It's one of my favorites. And the same is true for if you want to prove Floquet's lemma, you can do it in the same way. Of course, there are many ways to do that, but here's the proof. Okay, so we're going to derive the homological equation. So we'll say dx v equals av. That's our ODE. So that means dx of tz equals atz. That says dx tz plus t dx z is equal to a t z. And now we put in what dxz is, our goal is to make that a plus z. Okay, so now let me write this out. Notice that now everything has a z. This has to be true for all z, in fact. Right, because I can give any data I want. If this coordinate transformation is to do what I say, it has to apply for this equality has to hold for every z. And that means I can just take z out of the equation. And that gives me this homological equation, which is dxt is equal to, now it may look a little bit familiar, at minus t a plus, which shows up all the time in numerics. And right, so it leads to Riccati equations and interesting things. Yeah, also in normal forms. Yeah, trying to find, or even in linear algebra, just trying to find a change of basis, right? All the time. Okay, but now I'm going to view, I just look at this in a different lens. Okay, instead of a matrix, n by n array, I'll look at it as a vector with n squared entries. And this says it's equal to some linear transformation applied to itself. Because I'm multiplying from the left, I'm multiplying from different sides. Both are linear operations on the matrix. And if you write it, so now it's this is a big n squared by n squared matrix effectively, and it looks kind of weird and it's very sparse. But this T is, I just take the columns of Roman T and I put them one after the other in a large column vector. So now I have n squared entries. It's a one. This is an n squared by 1 vector. And this is an n squared by n squared matrix operating on it. Well, I know there is one because it's a linear transformation. So I can always do this. And we've written these out plenty of times for various reasons. It's kind of amusing to do, to see the structure. But anyway, all we need to know is that it's linear. So now I'm going to view this as the previous problem, like a gap-Lemma type problem, but on this enlarged matrix, this lifted matrix.
Big A.
I could write it down, but it's actually, that would just obscure what we're doing, it turns out. It's better not to, because here's all I want to point out. There's an eigenvector of script A is the identity, which would be, okay, E1, E2 through En. The standard Euclidean basis written one after the other. How do I know that? Well, because I know the action of A is AT minus T A plus. I'm sorry, it's an eigenvector of A plus. At A plus, what is A plus? A plus applied to a matrix, going back to the other form that we know is still there, it's going to be A plus T minus T A plus. So this is the behavior at plus infinity. It's just a commutator of A and T. And if I take T equals the identity, it vanishes. So it's a eigenvector, it's identity, and the eigenvalue is mu plus of P is identically 0. So it's actually given to us as 0. We don't have to modify it to make it 0. It's just 0 from the beginning. So applying the gap lemma, we obtain a solution T of xp. So this is just oh, did I say? Yeah. This is T plus of P. It's this. T of xp is T plus times 1 plus order of T plus e to the minus theta tilde x. Let's put it like this. But that now, projecting down from the lifted description, that's T of x p is equal to the identity plus some theta tilde and theta tilde, which is just defined to be this piece, is big O of e to the minus theta tilde x. And that's what the statement of the theorem was. You know, I remember very clearly Guy was visiting and sitting in a little visitor's office, and we were trying to do this for, well, maybe we can do it for the diagonal case or something, you know, some very special case of matrices. And we wrote this down and looked at it and said, but doesn't this work for all the matrices? That's very strange. It's something with almost no work. You get a lot. Just viewing it from a different perspective. This is completely equivalent to the gap lemma, and yet much more convenient. Okay. And that, yeah, it's almost a tautology, but that's one of just the main tools in this business. Okay, so let's see. Perfect. Okay, so that's the exact end of that part. So let's take a 5-minute break and we'll come back. Come back.
So T is identity, so it's almost like this transformation is the identity.
Yeah, it's near a near identity transformation. And also we get, let's see, we get that it is invertible as well. I guess that's just by a Wronskian computation, for example.
Like you have normal forms, you make transformation, identity, something, and it don't take all.
This is
It gives you coordinate.
right. Yeah. Yeah, so that's very familiar at high frequencies, right? People use this for WKB and normal forms. But yeah,
The simple.
yeah, simple version of it. Yeah. We could write the, we know that this is global, so it's a linear equation. It has a global solution. What we write down the equation on the inverse t, it looks almost the same. And it also,
Ça te va. Et t'as vu, il y avait le message d'Emmanuel là.
I think there is.
Oui, faut que je regarde mes dates.
Toi, tu viens, toi, tu vas au premier, moi, je vais au deuxième.
Oui, c'est ça. Et je vais aller au troisième aussi, je pense. Fin juin, début juillet.
Yeah, I think I
Il
just.
y a le dispersif juste avant.
Mais il y a le dispersif.
In person T. I think just the sign change. And again, it's solvable. Down to zero. That's again, T is an explanation. Yeah, that's good. Okay. So you sort of get, yeah. It wasn't, I think I did oversimplify. It's pretty simple, but I oversimplified.
What do you expect, for instance, in the Lima, instead of the exponential decay of the perturbation, you have polynomial decay?
Yeah, that's tricky. Yeah, so if it's, yeah, that's hard. If it's an L1 perturbation, okay, then you could apply the theory of Coppell, but you need a gap. Now you need a spectral gap, so you're a bit limited.
Okay.
And if it's not, so a student of mine, Peter Howard, he's the chair at Texas A&M now.
Oh, okay.
Yeah. Yeah. So he, I gave him this problem to treat the case of 1/x decay. It's not, it comes up in detonation waves. It's an important case. He treated it, and you could look at, see what he did. It worked really hard.
So in that case, with the corollary, I mean, like, what would you expect if you also, if there's any positive result there, it also translate to the corollary that you get?
Oh, that's interesting. Yeah. So from that one, there's something like a gap lemma.
Yeah.
But I think you're asking, is there something like?
Yes.
That's a good question. That's a great question, because when Peter Howard was doing his work, we didn't have a conjugation, so he didn't try. But maybe you could. That would be great. Help a lot. That's a. That's good for you. And so, you don't get. So suppose you wanted to do this, let's see, I think in order, so we've got this one eigenvalue. To use Coppell's trick, not trick, is proof. You need it to be a simple eigenvalue. And that means that the eigenvalues of a plus are distinct. So now you have a lot of. It's a stronger something. All of them must be simple. You have spectral gaps between all pairwise spectral. But a lot of times this. You have a particular problem in mind?
No, not really. Because, yeah, I think I do. I'm always interested in this sort of, like, stability questions in different things.
Yeah, well, me too. Yeah, different. Yeah, that's an excellent question. Don't know the answer. But I'll write down. So it's Peter Howard. WARD around this Dalston ball or so. Ball. Yeah, fantastic thesis. And then I gave him this problem, which was supposed to be a small variation on that. It was so hard that it took up like 3 years to do it. It's really a good work. And, but it was very special.
And it's they receive an email with the grades and stuff, and also I don't need to carry the booklets around, so it's
I have 180 papers in a room in my home, and I have to bring them back.
that's why I'm a CrowdMark supporter because we don't want to do that.
So I think I'm going to take a big luggage and bring
Oh,
them back and have.
There's a cut. I
No,
think
but I
so.
have to bring them here first.
Yeah.
From my home, I have to
Oh, yeah.
I have to take the car, not the subway for that. It's
First.
my exam last term was from 7 to 10 at night. So I had
Carry that luggage home. Ah, my goodness.
smart.
I see an instructor made it.
I never paid 188 papers. That was the first time.
Hmm. Slim still. Yeah, I shortchanged you. That was a good question about the inverse, Federico. Here's how I answer it. If I want to find the equation for the inverse, I use the derivative formula for matrices, which says it's negative T inverse dxt T inverse. I know I have this sort of commutator for the derivative of T, and now when I multiply this out, I get the reverse commutator for T inverse. I get an equation that's almost the same, but I don't really care what it is other than it's linear. So there's sort of a duality. Because for a linear equation, I know I have global existence for ODE. So I can integrate both of these all the way to 0. And this relation actually ensures that T inverse is the identity all the way.
I have another question.
Uh-huh.
How do you construct what's the equivalent system? You have a system for capital T.
Uh-huh.
Then what's cal T? And
Okay, so let's do, okay, yeah, maybe let's try a small one and just see how it goes. Okay, so let's see if I can do this. Okay, so I'm going to take script T is going to be T11, T12, T21, T22. Yes, no. Yes, that's what I want. I want to just write the matrix in, oh no, I said I wanted the columns. Maybe it's easier with columns. Okay, so T21, T12, T22. Okay, and now I want, okay, so AT should be AT minus T A plus, and then, made calligraphic. In other words, I want to write down the first column and the second column. Okay, so let's see. I may have, okay, let's just try. So this is going to be, what does this look like? It looks like, this one looks like AT1. That'll be the column, first column. Minus T1. Oh, now I'm already getting, let's see. I'd better write them out. Okay, so let's just write A11, T11, to T1, T21. Right. No, I want the columns. Oh. Yeah, so it's going to be a T1, a T2. Okay, this one's going to mix things up a little bit. Because now I have the row against this. And then I have to take, let's see. Oh, except I just want the first. Let's see. That's what I want. Trying to think of a simple way to write this. Oh, okay, I think I don't have the block structure in mind, but you see, you multiply this out, you take the resulting columns, and you put them one over the other, and that's your answer. But yeah, so if A is 2 by 2, then script A is 4 by 4. It's not so bad. Yeah.
Was n squared by n squared.
Yeah, N is 2. So for 2 by 2 is not so bad. We could write it out, but
Yes, 4 by
I'm botching it, so I won't. Yeah. The trouble is, yeah, it's kind of it tries to resist block structure because it's in reverse order. But yeah, you have to write it down and sit down and do it, I think. So if you'll allow me, I'm just going to pass on that one. Okay. So now an application. This was for looking at the resolvent equation. So let's see what we can do with it. Okay, so first of all, it's second order. So, and the theory was, as usual, it's for the first order system. It's easier to deal with. So, but we can always change to we can rewrite it as a first order system. A first order equivalent is to take v dxv as the variables, and then dx of v dxv minus 0 identity v dxv. Okay, the first row is immediate. I get a 0 on the right-hand side. I'm going to get an f over here if I do it right. This should be lambda plus dx a bar, and this should be a bar. And that's the usual trick. And so we'll call this even though it's not the same as the previous, any kind of lifting, I'm just going to call script A, and we'll call this script V, or minus script VA is script F, and script F is 0 little f. It has kind of a special form, but it doesn't matter at all for what we're going to do. Okay. Now we're going to apply conjugation lemma. So this is going to give us t plus on x in 0 plus infinity, t minus for x on minus infinity to 0. Two different transformations that change this equation star into constant coefficient. So this converts star to star star. Okay, star star is dx z minus a plus, okay, let's say a plus or minus of p z. And here, what's our parameter? P is just lambda. There's no other parameter in this setup. And this will be, okay, so f plus or minus, and that's, okay, and that will be, that's going to be t plus or minus inverse times 0 little f, if you want to know exactly what it is. Okay, and now we're going to, we have star star, but then we also have a very important fact. We have, so we solved the equation on 2 half lines, but then we have to connect it. So it's important that we require the matching condition. Okay. And this comes from V equals T Z plus or minus. And these are equal at the common point x equals 0. They have to agree. And that tells me that, okay, that tells me that z at, so z minus at 0 minus, with a t minus is equal to t plus z plus at 0 plus. These have to be also. So I have 2 different variables. They live on the opposite half lines, and they must have this matching condition, which I could also write just as z minus of 0 is equal to t minus inverse t plus z of 0 plus. So 0 minus to 0 plus. And I could call this M. There's a transmission matrix now that relates them. So in the original variables, it was just matching. V matches at the common point. But in the new variables, it's different. It's something else, and something that we have no idea what it is. The only thing we know is it exists. And we know that because the inverse is well defined. We just discussed it, all the way down to 0 and bounded. So this is just some matrix conditioned.
T minus is just a straight T, no? It's not back to this calligraphic T.
No, this is a sorry, okay. This is, I'm sorry, this is a okay. Well, now I'm running out of letters. Maybe I should have made these something else. This would be, yeah, some other. It's calligraphic only because Z is calligraphic. Yeah, it really shouldn't be. It really shouldn't be, but yeah. Let me leave it bold. Okay, it's going to act on the calligraphic, guys. Augmented, yeah, because I wrote it as first order. It's a phase variable system instead of the original variables, which I needed in order to. I mean, all these things I did, I used heavily that it was first order, to solve by variation of constants, etc. It doesn't, yeah, work so nicely in higher order. So this is standard. Okay. And so now we have two constant coefficient problems and a boundary condition. And the boundary condition is kind of unknown. This is a matrix that depends only on lambda, or let's say more generally M of P, but it depends only on lambda. And it's on 2n by 2n. So it's in complex numbers, 2n by 2n. It's a complex matrix because lambda is complex. And that's what it is. Okay, so now we need to solve it. Well, if you've worked with constant coefficient ODE with boundary value problems, you know that the enemy of a solution is if you have imaginary eigenvalues. You won't have a nice bounded solution. You need a spectral gap. Your A matrix must have a nice spectral gap between, so we need no center subspace. For the coefficient matrices in order to solve. And we'll see that quite explicitly when I write down the solution formula. But up to now, let's just take this as for granted. We'll see why it is in a minute. But here's lemma. So A plus or minus has non-trivial center subspace. If and only if, this is for our A plus equals A plus of lambda. If and only if lambda is lambda j plus or minus of ik. So one of these dispersion curves lies on a dispersion curve for W plus or minus. So I'm relating back to these dispersion curves again. And it's kind of illuminating though. This proof is pretty nice. And yes.
In the boundaries.
Oh, lambda j of ik. So these dispersion curves that we drew, these were lambda 1 plus of ik, lambda 2 minus of ik. They were dispersion curves. I'm sorry, that is, lambda lies on a dispersion curve. So in other words, we've shown that these dispersion curves are bad. They have essential spectra. But away from those, at least we have a spectral gap for our matrix. And here's how you show it. Okay. From the format, did I write it down? Let's see. Here it is. Star. This is the formula for A. So we have A plus is zero identity lambda A. Yeah, there we go. Just all that I'm lacking is the derivative term. And so if we have an imaginary eigenvalue, that means that, well, the eigenvector is equal to R mu R. How do I know that? Well, I know that by the construction, by the phase space construction, I know that this corresponds to the derivative of this. And I know that if I integrate that, let's see. No, I know that this is the derivative of this in the integrating the ODE. But it's yeah. I know there corresponds an exponential solution E of the original equation with this derivative. Okay, so you can verify this algebraically. This has to hold. You just put you put in R and some unknown, you'll find this is the unknown. Okay, but this is now I plug this in and I find that IK times R IKR, let's see, is equal to A plus RIK. And this tells me magically that IK V, sorry, lambda plus IK V minus K squared V equals 0. I find that it solves the dispersion relation. Just because I'm just undoing, I wrote it as the first order, the second order system as a first order. As soon as I put an eigenvalue in here, it goes back to essentially a second order system. And then I noticed that because I chose the eigenvalue to be IK, well, it's exactly like the Fourier transform. The derivative is IK. So I just get the symbol. Oh, times R. And so this is an eigenvalue of the symbol, Fourier symbol, and therefore it's in the dispersion relation. Oh, I'm sorry. IK, this should be these should have all been times R. I'm sorry, there's no V. The R is the V. Yeah. Let's see, what did I leave out? RIKR, thanks. Yeah. If you write this out, you get just the Fourier symbol, and therefore R and lambda. So now looking at things the usual way in terms of time coordinates and with K as the parameter, we see that lambda must be on one of the dispersion curves. So that is how they link. And this comes up all the time. Sometimes the lambda J are called temporal eigenvalues or temporal modes. and the mu j of lambda are called spatial modes or spatial eigenvalues. These are the eigenvalues when you consider the resolvent equation as a function of x, and if you consider it as a function of t, then these are the familiar, the dispersion eigenvalue, the eigenvalues for the dispersion curve that are more familiar. This is like Laplace transform, this is Fourier transform. So it's natural. Okay, so at this point, right, so I know now where I have a spectral gap and where I don't. I lose a spectral gap exactly on these spectral curves. Now, what happens in between? Okay, but I should, yeah, okay, so, all right, so any questions about this part? It's just manipulating some algebraic symbols. Well, let's see, let's just, we could just write it out. 0, I, lambda, A plus, R, mu, R. Okay, so we're going to get mu R, and we'll get lambda R plus A plus mu R. And that is supposed to be mu R, which it is, and mu squared R. So the first equation is automatically satisfied. That's because of the augmented system. And what is the second equation? If we write it out, it's mu squared, sorry, lambda plus A plus minus mu squared times R equals 0. So there's a first order guy. And now there's a mu here. That was a mu. And now I just substitute in IK for mu. Oh, what was oh, sorry. Star is where's star?
The equation for the vector phi x.
This star, yeah. This is, oh, you mean this star? The original star? Okay, yeah. But now I'm only looking at the matrix at infinity, the limiting matrix. Yeah. Right now I'm only talking about the limiting matrices because that's all that's left. I've transformed away all the spatial dependence. And now I only have to talk about limiting matrices. And that's all I can talk about for the z coordinate because that's the only thing there. There's no more A bar, just A plus and A minus.
The first line has non-trivial center subspace. How this, because that is hypothesis if and only if.
If and only if, yes, because when we write down what it means to have center subspace, okay, so let's see, I just did the calculation showing that for any eigenvalue, this is the relation. So it reduces to a second order problem with mu corresponding to dx. But if I have a center subspace, that means mu equals ik with k real. And when I substitute in mu equals ik, this becomes the Fourier symbol. Oh, if I have no center subspace, I automatically have.
You have not your center subspace if you are relying on this parabola.
Right. Yeah. No, you don't have it on this curve. Yeah, but right. Yeah, having a non-trivial center subspace is equivalent to not having a spectral gap. Yeah, right. So I'm identifying, so trouble spots are going to be where you have a center subspace. And we already know, but we already knew they were trouble spots by a different argument. We already know this is essential spectrum. It can't work. And yeah, so it turns out though, if you do have a spectral gap, then it usually works. Things work out. So that's the next step, is to look at, okay, how do we then solve the equation?
center space correspond existence of eigenvalue on the
On the imaginary axis, any value. So it could be any ik. This is why I take ik. Mu equals ik. For a hyperbolic system, yes, you would be really stuck, right? You would have all spectra on the imaginary axis, and you would have to move away from the imaginary axis to be okay. And you would get at most bounded stability. You won't get any decay. There's no hope. And that's what people prove is well-posedness for hyperbolic equations. There are hyperbolic systems that are not conservation laws, that have damping of some sort, and those you can prove exponential, not exponential stability, but depending, yeah, you can do something. But first you have to move off something has to move you off of the imaginary axis. You're exactly right, right. Yeah, so I've been mentioning hyperbolic systems sometimes. Those are the ones I mean, the nice ones. Yeah. Okay, so now comes, well, it's the Lyapunov-Perron again, because we're solving a boundary value problem. So we'll just do it by, let's see, okay. We'll do it much the same as we did in the gap lemma proof, but now it's not. You'll see, it's not a contraction mapping. It's just a linear system. Okay, so this was A, by the way. A was to connect the spectral gap to this dispersion curves and see what's going on. Now, let's convert to an integral equation. And that's Lyapunov-Perron again. So, and here's how we can do it. So we've got dx. Let's just do, let's do plus infinity. And write it down. So we have b of x is equal to, okay, e to the a, the stable part of a, so the projection onto the stable subspace, x, and times the stable part of v0. So we're going to initialize the stable things with a value at 0, which we don't know. The unstable, oh, sorry, and here's the rest of the stable guys. Now we have to put in the, okay, so there really, let me just put the pi s like I did before. And now this is exponentially decaying. Strictly, because I assumed there was a spectral gap. So all eigenvalues either have a positive real part or a negative real part. I'm dividing them into those two classes. The strictly negative real part are the ones in the stable projector, and the strictly positive are in the unstable, and I haven't written that down yet. And it wasn't even necessary for me to put an unstable or stable part there. I could have, in fact, I shouldn't. Let me not. So I can write the solution this way. And notice that everything in sight is exponentially decaying. This is going forward, and this is the stable part, so it's decaying like e to the minus theta, absolute value of x. This is x minus y is positive. Okay, again, this is e to the minus theta, x minus y, absolute value. This one's going in the reverse direction, but it's unstable. So this is order of e to the minus theta, x minus y again, because this sign of x minus y is now opposite. So everything's got a good exponential decay. And this is in fact, okay. Yeah, so we can from this nicely estimate the say the L2 norm of f by Holder. Just take the L2 norm of this whole quantity of each integral is bounded by the L2 norm of f times the L1 norm of this exponential decay, which is bounded. So this gives me a nice bounded operator, mostly. And there's only one problem. I don't know what this is. This is somehow going to be determined from f plus, because, okay, if I know the stable value at 0 and I know f plus, then I know everything. But I don't know this. There's another formula on the negative side, which gives me v unstable. This is likewise v unstable of 0 plus is unknown and needs to be found out.
Return original.
Oh, I'm so sorry. Yeah, everything is a z. Yeah, yeah, everything in sight should be a z. Yeah. But luckily there weren't too many z's. Yeah, only one. Yeah, z. Oh, yes, yeah. Yeah, this is z. Yeah. And so it's, yeah. That's, yeah. And that's the point. Well, there's only one hope, right? I have a matching condition. I mean, this problem is not, it's not well posed without the matching condition. You can see it. I could have any value of zs and I would have a nice solution afterwards. It's quite non-unique. This is where I use the box, right? Okay, so I notice, yeah, so the box says, which is, I guess, yeah, say M for matching. We have, okay, z of 0 minus is equal to m of lambda z of 0 plus. But we don't need all of this. This is, okay, z of 0 minus is z, okay, let me be careful here. So 0 minus, I want, oh, this was 0 minus. I want z unstable and z stable. And this is invertible. We know that because T inverse T is invertible. And this is Z stable and Z unstable of 0 plus and 0 minus. And the ones we really care about are Z stable of 0 plus and Z unstable of 0 minus. Those are the two that we need to find out from this relation. And the others are determined as functions of f and z of 0 of u and z unstable of 0 minus and z stable of 0 plus.
Excuse me, I'm not what ZS that you means.
This is just the stable and unstable part. So I project z onto the stable part, the stable eigen modes of the matrix A minus and the unstable modes of A minus, and then likewise on the other side. But I noticed that this is a function of this and F. This is a function of this and F. So I can write this as some okay, some little m equals some n of F. After rearranging things. This comes from, I know if I have a relationship like this that is invertible and that and these are functions, the unboxed guys are functions of the ones in boxes and F, then I can rewrite it in this form where, okay, I don't know what this is, but it's something. It's not that closely related to big M. It's just inherited by solving this big M relation and taking into account the dependence of the unboxed traces on F and the boxed ones. So it's complicated though. It's quite complicated because to find the dependence, I plug this in, I solve this integral equation, and then I evaluate at 0. So this one's gone, but this one is here. So it's an integral equation, it's an integral dependence on F. Yes. Because I have equations such as this, and let's just look at this for a moment. Okay, so what if I want to find the unstable value at 0? Okay, this is in the stable subspace. It's not part of that. It could only be, and so is this. It can only come from this, and it's with x equals 0. So that's an integral from 0 to plus infinity of, well, it only depends on F, actually. Doesn't depend on, I misspoke. It does not depend on the other one. So that goes over onto the n of F side, which is just two vectors. Yeah, so I substitute for this and this, some functions, some linear combination of, some linear functions of F minus and F plus. I rearrange, I will always get something of this form. I could explicitly write it down, but it's not super explicit because it's an integral operator in there. But for what I'm going to say right now, it's not super important what it looks like. It's just that I want to have a unique solution. And what do I need for a unique solution? I need that, well, I need the right dimensions, first of all. So I need that these dimensions, this should be a square. So this is n by something, right? We don't know exactly what it is, but sorry, 2n. Is that exactly right? Let's see. Well, basically, I need that these two dimensions add up to n. This is what I need. I need that dimension of Z of the stable subspace plus dimension of the unstable subspace on the plus side. Is n. I need that they add up to n. In other words, I need that the stable subspace of A has the same dimension on at both infinities. Otherwise, it's just a non-square matrix. I'm not going to be able to solve that uniquely. So just by dimension count, I'm in bad shape. Now, it could be that there's some redundancy that allows me to solve it, but okay, that would be generically, I need it to be square. Okay, this condition is called consistent splitting. That's Alexander, Gardner, and Jones defined this term, and it says the dimension of the stable subspace of A plus is equal to the dimension of the stable subspace of A minus. Once I have this, I have a nice square matrix here.
Then big expression.
Yes.
So if that of x positive, but is it,
Yes.
it's on the left, it's expressed only in terms of z stable, then s. And
No, this is both. This is both. This is both stable and unstable. This is both together. The stable part, and let's look. What is the stable part? The stable part is well, at x equals 0, I can tell you the stable part. It's this. It's because this becomes identity, and this is integral from 0 to 0, and this is all in the unstable part. So I know this really is the initial condition. I'm initializing the stable component, but I don't know what is the unstable component at 0, except that if I hit it with the unstable projector, that kills the first line and leaves only the second line, and I'm integrating from 0 to plus infinity, something everything's known here.
I mean, that unstable of 0 plus
Yes. Yeah, that's how I know
this one.
that all of those things can be put over on the other side as functions of f plus or minus, and then I have this left. Okay, so there are a couple more things to say here. So so let's look just at our picture of our dispersion curves. Okay, off towards plus infinity, it's pretty easy to determine that the stable subspace has dimension 1 and the unstable subspace has dimension 1 on both sides. It's because it's dominated by, you could forget about the off-diagonal term. It's actually dominated, the spectrum of this matrix is dominated by the spectra of 0, 1, lambda, 0, which is a nice hyperbolic matrix with eigenvalues plus or minus square root of lambda that for big lambda, we can forget about this O of 1 term. So we can compute that consistent splitting holds out here. And right. And so it also can be seen to hold here, curiously. But in here, there's something, that should be all some kind of essential spectrum, but what kind? It's like a very dispersed, it doesn't have a curve measure. It has a measure on space, a spatial measure. So that's very different from self-adjoint operators, where we expect when we talk about essential spectrum as just continuous spectrum, thinking of a curve, at least I do. But this has essential spectrum that involves curves, but also is supported on regions of non-zero measure. Okay. So we can define another definition. The Evans function is defined as d of lambda defined as determinant little m of lambda. On the region of consistent splitting. Automatically. Because all on that region, why is it important that I be on consistent splitting? Well, notice this formula depended on a specific splitting into stable and unstable modes. If I cross one of these lines, the projectors change. It would not be analytic crossing over a curve, even if it happened that these two curves coincided, as they can for some cases, so that it was all, so I'm just hopping across from consistent splitting to consistent splitting, the Evans function would change because the formula changes. And this depended on separating out the plus and minus modes in a special way. It doesn't even make sense if you jump across the curve. But now, so long as M is uniformly invertible, I actually have a unique and bounded inverse. I have a resolvent point. So the proposition is, on a domain of consistent splitting, I'll just approximate it like this. Rho of L is equal to set where determinant of M does not equal 0. And spectrum of L is equal to the point spectrum of L. Or all points are in the essential spectrum of L. Okay, for our particular case, I've already excluded that. Have I excluded that? No, I haven't quite excluded that. I mean, I know because why? This is an analytic function. Its zeros are isolated. The inverse of this function is meromorphic because it's a rational function. Sorry, it's not rational. It's a ratio of cofactor matrix and determinant. So two analytic functions. Therefore, it's meromorphic. Therefore, any zeros would be of finite multiplicity. So it actually is playing exactly the role that the characteristic determinant played in the matrix case, in the finite dimensional case. And it can be shown with proper normalization. This is a Fredholm determinant for something, if you're careful. But it's finite dimensional. So we found out a lot. It wasn't clear that, that anything should be meromorphic before now, but now it is, because we have such a concise, well, maybe not concise. You might not consider this concise. It's in principle concise, right? Because it's an algorithm for finding the solution. And with this algorithm, we could, in principle, estimate anything, because it's all constant coefficient. And we will have to estimate a few things. But for right now, we've just proved Henry's theorem. Because to the right of all the essential spectrum curves, we have either two cases. Either there's no point in the resolvent to begin with, out here, in which case it's filled with essential spectrum by definition, or there is a point in the resolvent set, and therefore we have, right, because the analytic function, the determinant, could vanish everywhere. We don't know that it doesn't. But once we know it doesn't vanish everywhere, then it's meromorphic. And that means there's no more essential spectra to the right, that was part B. that we were trying to prove. So that's the end of Henry's theorem. And good, because that's the end of the time slot. But yeah, so next time we're gonna do another theorem of Henry and Sadinger, which shows how to deal with the problem of essential spectrum coming right up to the origin. So now we know that's all there is, and we're going to try to get rid of the rest of it in some way. Okay, so I stop there and take any questions.
Hi, Kevin.
But yeah, so far we didn't really do any computation, right? We just showed you could formulate it as a linear system. And from that, you extract this Evans function, and that's crucial. And some dimensional conditions, which gives this consistent splitting, this Evans function, and now we'll go on.
Kevin,
Yes.
so what about the point that not satisfy the consistent splitting for those lambda? They must be point spectrum or?
No, that would be some kind of essential spectrum, because if you think about what it's actually reduces, now this reduces to a problem in matrix algebra.
Mhm.
When is this problem uniquely solvable?
Yeah,
I first of all need a square matrix for that to happen. Otherwise, it's not even unique. And if it doesn't have a unique solution, that automatically puts it in the essential spectrum.
Sorry, I have to teach.
Yes.
yeah. So there's not only a point spectrum, but also maybe when the consistent splitting doesn't satisfy, there may be essential spectrum that is on the right of this eigenvalue space.
Oh, you say if consistent splitting were not satisfied, yes, we would
Yeah.
have a problem. Right.
Okay.
Yeah. But then your equation would be, the original PDE would be ill-posed.
Okay. So usually it will satisfy.
Yeah, it's right.
Okay.
Always satisfied, because if you have a good solution theory, a good linear solution theory, then Hiller-Yosida theorem says you have resolvent points all the way, everything to the right of everything with real part bigger than or equal to some value is
Yes.
in the resolvent set.
Yes.
So if you don't have resolvent set out there, you don't have any bounded linear theory. You don't have a linear existence theory for the
Oh,
PD.
yeah.
So that wouldn't come up in
Condition
cases we
doesn't
look at.
depend on, this condition doesn't depend on lambda, right? It's just A plus and A minus. So
Yes, right.
so as long as there's one point there is fine. That's what you mean.
Yeah, as long as there's one point, and there always will be one point
Yeah.
if our PDE were well posed,
Okay.
linear level.
Okay. Yeah.
Mhm.
Thank you.
Did you use the, so you have Z plus or minus SU. So with the little m, you were able to solve for two of them.
Mhm.
The other two, which were the box, what happened to them and what do we do?
The ones in the box, these are the ones, they're supposed to be the ones, oh, I wrote the wrong ones. Let's see. Oh, the ones in the box we need to solve for. Did I write it backwards? Let's see. ZS at U plus should be, oh,
Which one are the important ones?
this was the minus, these are we were trying to solve for the ones in the ones that appear here. So it's stable at plus. Did I write it? Yeah, it should be. I reversed them. It's stable at plus on the plus side, unstable on the minus side. Yeah.
This little matrix M allows you to find them.
Yes. But nothing tells me this M is invertible, and we know sometimes it isn't, because there can be eigenvalues for operators. But it does tell us that it's invertible except at isolated points, just by the fact that it's analytic. So it gives a lot of information with no computations.
And once you know these two quantities, what do you do with them? Because you will have this expression explicitly give you that.
Yes, right. So then I have a resolvent bound. And remember, that is what I needed to get my stability estimates. I just needed resolvent bounds. And this says I can get them, but it's a little, I'm going to discuss this more later, but it's a little bit subtle in that, yes, this gives a bound, but it depends on lambda. It depends on everything. So on a compact set of lambda, this gives a uniform bound. But what about high frequencies? Let lambda go to infinity along the imaginary axis, then it's not clear, right? So you have to get those in a different way. But there are very easy ways to do that. Energy estimates, or, well, okay, there's an easy way, which is energy estimates. And there's a hard way, which is WKB, which we, a high frequency asymptotic ODE analysis, which is like this, but as lambda goes to infinity. This is the bounded lambda version, and x goes to infinity. And the other one is lambda goes to infinity and x stays frozen, basically.
Which one do you? Do you do the one with the
I've done both ways. Yeah, if I want all the information, I do the WKB because, I mean, it gives you a complete, almost like a solution formula. But if I want to make the analysis simple, I use energy estimates. Yeah, WKB is really fun once when you don't know what you're going to get. But then afterward, when you sort of know what you'll get, but you still have to do it, maybe less fun. So then I started looking for shortcuts. I'm giving you the shortcut version here. Yeah, I won't need to do any high frequency stuff.
maybe it's very elegant.
That's true. But there are even more symbols, like it's doubling the contraction mapping arguments, doubling the symbols. Yeah. So,
In this context.
yeah. Yeah.
In the con-
Oh, it's beautiful. Yeah. Yeah. And powerful. But it does involve at least this many computations, wouldn't you say? So, whereas an energy estimate is just one line. Yeah. Also, we have to do an energy estimate anyway. So it conserves. All right. Well,
non-territory, right?
yeah.
Okay.
Yeah. That's I think among PDE people, you can safely do that. Yeah. 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 Well, thanks. Yeah. Thank you for your yeah. See you in a while. See you. Let's see. There is one coming up on Friday. Colloquium in the department? I didn't see. Maybe, I think there was someone, pure like algebraic one, or I think I saw that. Okay. Oops. You guys are still here? You're very patient. Thank you. How's it going back there? How's the temperature? Oops, I think it should look this way, right? Yeah. I
It's
can't.
still cold,
Yeah, super cold.
but it's fine.
Uh-huh.
Warming up. Yeah, it's fine.
So, okay. I have to do a transformation from the Gallo side is better and better means colder and colder, and probably the other people are the reverse. Anyway,
Yeah.
all right. Oh, okay. I have a call from Indiana, actually.
Oh.
All right.
See you later.
All right, bye.
Oh, hi. I just leaving the classroom, and I will talk to you in 1 minute because I'm grabbing my materials and it's blank. Oh, no, because, remember, I'm in nothing. So you can't very well, go to my office, but, really, in one moment, I'm quite available. Just putting things in my bag. All right. No. Yeah, so, oh yeah, so this always, this quick,